As shown, a wire loop is immersed in a uniform B field. The B field changes from 20 Tesla to 5 Tesla in 3 seconds. The loop radius is 25 centimeters. Determine the induced voltage. So the diagram here, you can see the loop. We got a green loop here. And these circles with the crosses, this is showing the direction of the magnetic field. And of course, it's into the screen. So we want to determine the induced voltage. Of course, there's going to be an induced voltage because the flux passing through the loop is changing. Since the magnetic field is changing, that means the flux is changing. That means there's going to be an induced voltage. This is just an application of Faraday's law, which we know is V equals change in magnetic flux over the elapsed time. And magnetic flux is magnetic field times the area times the cosine of theta. Okay, so I need to know how the flux is changing. Now, I can write this out. I'm going to show you just a little simplification here. We're looking for this. And so technically, this is going to be the final minus the initial. So that means I need to know B final, A final, cosine theta final, minus B initial, A initial, cosine theta initial. Okay, but some of these things aren't changing. The magnetic field is changing, but the area of the loop isn't changing. The radius is holding constant, so the area isn't changing. So these are the same. Also, this angle, we're not changing the orientation of the loop with respect to the magnetic field, so the angle isn't changing. And so this actually simplifies down. So you could think of it as I pull the area and the cosine out. Those don't change. And so what I'm left with is B final minus B initial. And as I said, I'm pulling out the area and the cosine. And so this really just becomes delta B times A times cosine of theta. So when we do this change, let me write this down fully. When we do this change, this is this operator, and it operates on this expression. Okay, things that stay constant, it doesn't act on. It only acts on the thing that is changing. And so we get this nice simple expression for what the change in flux is going to be. Okay, so I haven't calculated the area. Calculating the change in magnetic field, that's going to be pretty straightforward since we have those values up there. And we know the elapsed time, that's told right there. But we need to calculate the area because we're only told the radius. And I haven't figured out the angle yet. So remember that this is the angle between the magnetic field and the normal to the area. Okay. So the normal to the area, I have two choices. It can be into the screen or out of the screen. Those are the choices, into the screen or out of the screen. And I mentioned in a previous video that typically it's arbitrary which one we choose, but to keep things simple, we usually pick the one that's going to make the flux positive. So, or more specifically, make the cosine function positive. So my choices are either 0 degrees or 180 degrees, because the magnetic field, of course, is pointing into the screen. So I'm going to choose the normal that's pointing into the screen so that this angle is 0, because both the normal to my loop and the magnetic field would be pointing the same direction. So this is 0, so that simplifies this even further because the cosine of 0 is 1. And so this is going to just become, for this particular case, I'm going to go ahead and put in the values. So it's technically 5 minus 20, because it goes from 20 to 5. And the area, it's a loop, so this is pi times r squared. I'm going to convert to meters, so it's 0.25 squared. And then I'm taking the cosine of 0 degrees. And so when I do this calculation, I'm going to get, let me do my calculator real quick. This works out to be approximately negative 2.945, and this would be Weavers. So that's the change in flux, and then I need to divide it by the elapsed time and take the absolute value to get the voltage. So that's straightforward enough. So my voltage is going to be the absolute value of negative 2.945 over 3. And that means my induced voltage is approximately 0.9817 volts. Now, when I did this calculation, I actually still had the whole value here in my calculator, not just these 4 digits, but all of them. So it's possible this last digit might be a little different if you just take this and divide it by 3. But this is approximately what the answer works out to be. It's positive, of course, because we're taking the absolute value. So this is how we would do Faraday's law, how we'd apply it to this situation. In my case, it was the magnetic field that is changing. But of course, it could be, as it is for the problem below, I believe, the area could be changing, or even the angle could be changing, or it could be multiple ones that are changing. Typically, we only deal with only one of them changing, but there's no physical limit to that. Any combination of them changing is allowed. But that's it. This is how you determine the induced voltage. A couple other things I'll just quickly point out. The flux is decreasing, so that tells me that the induced magnetic field must be parallel to the external magnetic field. So I know the induced magnetic field in the center of the loop must be pointing into the screen. And since I know that, I already know what the direction of the induced current is, even though I haven't solved for that. Since that's going in, I'd use the right-hand rule, point my thumb down or into the screen, and my fingers are curling clockwise. So I know that I've got a clockwise current, induced current here.